Hello, this is Mr. K. Just going through a video which I think a lot of students have misconceptions in or errors in their understanding. So this is looking at the two different types of covalent structure. So 1.36, the syllabus statement from the IGCSE Chemistry course is saying, explain why substances with simple molecular structures have low melting and boiling points in terms of their relatively weak forces between, this being a crucial word here, the molecules. So forces between molecules, not within the molecule. And 1.37, explain the high melting and boiling points of substances with giant covalent structures in terms of the breaking of many strong covalent bonds. So to look at this, I'm going to show you some modeling software. So we'll look at simple molecular first. So here's a molecule of water. It has very strong covalent bonds, these two here. So the grey is hydrogen, okay, and the red is oxygen. Between the hydrogen and the oxygen, they're sharing an electron, and this is represented by this short little line here as a strong covalent bond. These dotted yellow lines represent intermolecular forces. Okay, more specifically hydrogen bonding, but we won't go into that. You don't need to know it for the IGCSE course. So these are the intermolecular forces. So I'm going to click start and I'm going to zoom out. And we're going to have a look at this molecule. The whole water as a whole. So here we have individual molecules. Okay, and notice I can pull this molecule away relatively easily. And I can pull this molecule away relatively easily. They're being held together by these yellow lines. The bonding within these two molecules isn't going to break. Despite how much I drag this hydrogen, I don't have enough energy to break this hydrogen off this oxygen. But I can move all of these away from each other. And this is turning to a gas. You've all drawn gases, liquids and solids before, and all I'm doing is moving the particles away from each other, okay, turning it to a gas. Now you can see that they're not moving around a lot, so they don't have very much energy to overcome these intermolecular forces. So even when I drag them away, like here, they're still moving back into each other. Okay, so just to highlight, for a simple molecular structure, to turn it from a solid to a liquid or a liquid to a gas, I just need to break these intermolecular forces by pulling this molecule away. This is a solitary molecule, a discrete molecule. Okay, this molecule is not covalently bonded to this one. They are separate entities, only connected by these weak intermolecular forces that you can see there, but they're not they're connected by strong covalent bonds. So this doesn't need much energy to break. It's right in our faces here. Now looking back at diamond, which is a giant covalent structure, and this will be 1.37, explain why they have high melting and boiling points. Again, I'm going to use a model. So here's diamond, which is comprised entirely of carbon. So we've got a carbon atom in the middle, and then 4 carbons bonded to it. Given that carbon forms 4 strong covalent bonds. Now just like the water, they are forming covalent bonds. The bonds are the same. Not quite the same, as in they're not between the same elements, but they are still both covalent bonds. Now this is a small cross section of diamond. I'll actually zoom into the bigger thing, which is over here. So here we have a much bigger version of diamond. Now what you'll see is, instead of the water molecules being individual and discrete and solitary, in diamonds all the carbons are bonded to one another. So you have to break, and going back to the syllabus statement, many strong covalent bonds. And in this case, you are breaking strong covalent bonds if you want to melt or boil this. Yeah? And I'll show you why. With the water, I could just pick up a molecule and pull it away, and it would separate. We'd break the intermolecular forces, but the bonds would stay intact. With diamond, when I pull these atoms away, they're still chemically bonded. I don't have enough energy to break them. Yeah, you can see that I can't separate these atoms from one another, therefore I can't turn it into a liquid or a liquid or gas very easily. I need a lot of energy, and I need to break all of these strong covalent bonds. And just to highlight that cross section that I showed you earlier, okay, here we have, let's zoom in a little bit more, or zoom out. Here we have a carbon atom, one strong covalent bond, another, one more, and the fourth. Okay, so they're bonded in one big giant covalent lattice, and to break these bonds requires a lot of energy, and it's the strong covalent bonds that you'd have to break if you wanted to turn this into a gas, because I can't just pull off, or even a liquid for that matter, I can't just pull these atoms away. Yeah. Whereas if we look back at the water, let's open it up again. Looking back at the water, when I want to turn this to a liquid, I just simply have to drag this molecule away. Yeah, and it's relatively easy. I just pull this molecule away. I'm not breaking a strong covalent bond. The covalent bond is between the hydrogen and the water, this bond here and this bond here. I'm not breaking those. All I'm doing is breaking the intermolecular forces. Whereas with diamonds, unfortunately, you are breaking these strong covalent bonds.